Okay, so we're going to go through one of the practice papers now for synthesis and analytical techniques. So first question is looking at synthetic routes, and I'm going to make a bromoalkane from an alcohol there. So how am I going to do that? Well, I've got to work out which conditions I need, and the conditions I need is an acid catalyst, so it's going to be A for that one. The acid catalyst actually makes this a better leaving group, which allows the bromide ion to do a nucleophilic substitution. Right, for question 2, you've got to do a little bit of adding up. If you add up the molar mass of ibuprofen, you get it to be 206. You're then going to convert the 200 meg into grams, which is 0.2. So divide the mass by the molar mass, and that will give you the answer B. So I'm now going to react this molecule with sodium borohydride. So the key thing you need to look at here is what functional groups do you have? Well, you've got a benzene ring. Do you know anything about benzene reacting with sodium borohydride? And the answer would be no. And you've also got a ketone here. And you do know about ketones being reduced by sodium borohydride to secondary alcohols. So the answer is B. Nitration of benzene, well, the only mechanism that you've met which involves benzene is, of course, electrophilic substitution. So the answer's D. So this shows the apparatus for reacting potassium dichromate with butane 1-ol, and we are distilling the product off. You can see that you are in the distillation setup there. So what are you going to do? Well, it's oxidation. So these are your two options, C and D. And because you're distilling, you're not going to have full oxidation to butanoic acid. You will, of course, make butanol. So I now want to remove an acidic impurity from organic liquid. What do I need to do? I need to get rid of that acidic impurity. So if you add sodium carbonate, that will neutralize it. So you're going to add sodium carbonate for that. So the answer is A. So I'm going to add now bromine water, solution of phenol. What would I see? Well, the bromine water, you're going to have an electrophilic substitution reaction to make 2,4,6-tribromophenol. So you are going to have the bromine go orange to colourless, but you'll also have a white precipitate form of the 2,4,6-tribromophenol. So the answer is a B. So you're now looking at which of these molecules are going to be most soluble in water. Well, you're looking at the ones which are going to be able to hydrogen bond the most. So you're looking for OH groups. So this guy has got 2 OH groups, but he's also got a carboxylic acid. We know that carboxylic acid is very good at H bonding, so the answer is D. So I'm now heating an organic compound with silver nitrate and ethanol. So if you remember back to your AS chemistry, this is because you're in aqueous silver nitrate, you're going to have a hydrolysis reaction. Because I've got silver ions there, I'm going to make the silver halide precipitate, and because it's cream, it means I've made silver bromide. So it's either going to be A or B, and of course we know that benzene, a bromine attached to a benzene ring will not undergo hydrolysis. This is the only chemistry that you've been taught that where you have a it's a cycloalkane, cycloalkane, but still it is a cycloalkane. So it's going to be C. Right, so we are now using sodium cyanide now with in acidic conditions, and I'm reacting it with benzaldehyde. So in that case, you will remember you make a hydroxynitrile. So that is going to be B. So this is an interesting one. How many peaks am I going to see in the hydrogen NMR for this one? Well, you notice you've got a mirror plane going down there. And these here are all the same. So that's going to give you 1 peak. But you're also going to see a peak for the hydrogen on those carbons there. So that gives you your 2 peaks. And remember, of course, you've got a couple of hydrogens on there, which is going to give you your 3rd peak. So the answer is B. Right, I've got a nice ester here. So what statement is most likely to be true about the mass spectrum of this ester? Well, if we start from the top, the peak M over Z45 is due to the fragment C2H5O+. Well, if you have a look, that there is C2H5O. So, and that is a likely bond to break, this one there, the ester bond. So I think that statement is most likely to be true. So A for that one. Right, it's got a nice polyester here now. So it wants me to have a look and see what monomers I am going to make. So hopefully you can see this is going to be the dicarboxylic acid there, and this here will become the diol. So the answer you're going to need are 3 and 2 for that one. So it's C. Number 14 then. The molecule contains an amine group. So which of the following statements are correct? So let's have a look. Does the molecule contain an amine group? Yes, it does, which is there. So 1 is correct. The molecule contains a carboxylic acid group. No, it doesn't. Because if that contains can you see you've got an extra carbon there between the carbonyl carbon there and the OH group. So that is not correct. The molecule contains an amide group, and again, that is not correct. So the answer is D. Okay, so we're now going back to the rate of hydrolysis of haloalkanes. Which of the following statements are true? A fluoroalkane gives the slowest rate. Yes, that's right, because the carbon-fluorine bond is going to be the strongest out of the carbon-halogen bonds, because fluorine's the smallest atom. The rate of reaction depends on the strength of the carbon-hydrogen bond. That is correct. The rate depends on the power to no way, Jose. That is wrong. So the answer is going to be B, 1 and 2. Right, so we've finished now the multi-choice, and we're now on to section B. And we're looking at alkenes. So we are taking an alcohol here to make an alkene and water. So what's the type of reaction occurring? Well, it's an elimination reaction. You can, of course, have dehydration if you wish. What's a stereoisomer? Well, I'll give you the defo there. Same structural formula, different arrangement of atoms in space. Now, we've got to draw these 2 types, 2 isomers. So your double bond is between those 2 carbons there. So we're going to put my double bond in like so, and then I've got a methyl group coming off one end like so, and obviously a hydrogen there. And on this carbon there, I've got a hydrogen and also a CH group like so, and and then coming off there, I've got 2 CH3 groups like so. So got CH, then I've got CH there, and then I've got a CH, two CH3 groups like so. So for the next one, we're putting my double bond again. Let's draw this the same, but we'll just put the methyl group going trans now. Now, it's also asked me to draw the other isomer here. Now if you have a look, you've got the OH group on that carbon there. So in theory, you could have eliminated a hydrogen from that carbon there, so your double bond would be on the end. So you would have had this set up like so, and then your methyl group there. So your H and OH, the elimination would have happened from there and there to give you your double bond. Okay, this is one for as part of the practical component of the course. So I've got to describe a method to just obtain my pure dry sample of alkene B from the reaction mixture, and also calculate the mass of alkene B that I would produce. Well, let's do the mass first of all. The MR of A is 102, and the MR of B is going to be 84. Okay, so first of all, let's look at how many moles of A we started with. So moles of A is going to be 9.26 over 102, and that is going to equal 0.0908 moles. Okay, but remember we only got 78%, 75% yield. So we're not going to get that number of moles of B. So moles of B that we're going to produce is going to be 0.0908 times by 75 over 100, which is going to equal 0.0681. And therefore, if you take that and times it by the molar mass of 84, of B, which is 84, you will find that you will get 5.72 grams of my alkene. Okay, what about purification? Well, you're going to use a separating funnel, which is going to separate your aqueous layer from your organic layer. You're then going to dry it with anion anhydrous salt, something like magnesium sulfate, and then finally you would re-distill the product. Okay, so we're moving on to polymers now. So we've got phenylethene. So you're going to have a benzene ring like so, and then onto that you're going to have your CH2. So let's do that like so, and you're going to have your H like so. Now what I'm going to do is I'm going to redraw that now, but I'm going to redraw it as an H shape. So let's do that. So get rid of that, and I'm going to put my C like so, H there, and H there. And then that shows, remember you're going to add across that double bond, so you'd have this going on. Just make sure that comes out of the double, of the brackets there. Excuse the dodgy benzene ring there. There you go. And that's going to be the polymer, and you're going to have it of end length. Okay, so how can we process these waste polymers usefully? We can't use landfill or recycling, so we are going to, we could combust them for production. Okay, so we now need to move on to question 17, and we are going to name hydrocarbon D. So let's have a look at the longest chain length. We've got 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be an octane of some description, and then coming off carbon 2, 3, and 5, you've got methyl group, so it's going to be 2, 3, 5, trimethyl octane. Right, so we've now got a calculation to get through. So we'll whiz through this. First of all, you're going to find your moles of hydrocarbon D that you start with. So you've got to convert your 80.4 tons into grams, which we've done there, and then convert that into moles by dividing by the molar mass of your hydrocarbon D, which is 156, gives you that. You've then got your 11 moles of carbon dioxide for every 1 mole of hydrocarbon D. So that's your moles of carbon dioxide. Pop it into your ideal gas equation. Remember to convert degrees C into Kelvin and your kilopascals into pascals. And Bob's your uncle. That's your answer. Okay, so we're now going to get an equation for the reaction of nitrogen with oxygen to produce carbon monoxide. So that's not too difficult, is it? Okay, so this is a lovely question, which if you get it, you're just telling them all you need to know about free radical substitution. So you've got your initiation step, then your 2 propagation steps, and finally a termination step. This is your overall equation here. You also need to say you use UV light, obviously, as your conditions. And also, what are some of the limitations? Well, you can get multiple substitution occur. So you may, this guy may go on to do further further substitution to give you 3C3H6Cl2, etc. And also you could also put the Cl on different parts of the carbon chain, so you could make one chloropropane rather than two chloropropane. So that's a general idea, but it's a lovely question about free radical substitution. Again, so this is a lovely question as well to tell me about benzene. So experimental evidence that led to development of the updated model from the Kekulé model, and we need to describe the bonding in the updated model. So first of all, the issues with Kekulé model, there were three, if you remember. The carbon-carbon bond lengths in benzene are actually all the same, whereas in a Kekulé model, you'd expect the double bonds to be shorter than the single bonds. The enthalpy change of hydrogenation is less exothermic for benzene than the Kekulé model would suggest it to be, which suggests benzene is more thermodynamically stable than the Kekulé model suggests. And also, if you try and react benzene with bromine, there isn't any reaction. You need a catalyst to get that to work. However, the Kekulé model, with those three double bonds, you'd expect it to undergo electrophilic addition very readily. So those are my three problems. How does the benzene bonding in benzene actually work? Again, this is just theory you need to learn. You've got your 6p orbitals, they overlap to form pi bonds above and below the sigma framework, and you have 6 pi electrons which delocalized around the ring. Right, again, this is a pretty lovely question. You're just going to make sure that you read it. So, of course, you're going to make 4-chloromethylbenzene, and you've got to show how you're going to use the aluminium trichloride catalyst. So, here you go. That's how the catalyst generates your electrophile, which is, of course, Cl+, like so. The Cl+ comes along and attacks the benzene ring. The electrons come out of the benzene ring to form a bond with chlorine. The bonding electrons in that carbon-hydrogen bond leave that bond and go into the ring to give back your 6 delocalized electrons and form H+. And then this is the final step in your regeneration of the catalyst. Again, it's nothing new, nothing particularly difficult. You just have to have learnt this really. Okay, so you've got to read this table and then kind of just draw how it's going to direct. So the first one says if I have a nitrile group on my benzene ring, how is it going to direct? Well, it directs to the 3 position. So this is carbon 1, that's carbon 2, that's carbon 3. So I'm going to put a Cl there. How about with this group here? Well, it directs to the 2 and the 4 position. So I'll make one isomer with my chlorine there, and the other isomer on the 4 position, which is going to be there. So it tells me that this molecule reacts in a similar way to phenol. So it draws the organic product that is formed from the tri-substitution of this molecule with chlorine. So if you remember from phenol, it goes on the 2, the 4, and the 6th position, like so. So that's your molecule there. So why does chlorine react more readily with this molecule than with benzene? Well, on this nitrogen atom here is a lone pair of electrons, which is partially delocalized into the ring. So that increases the electron density in the ring, and therefore the Cl electrophile is more polarized. Okay, so now I'm reacting lactic acid. Sorry, I'm not reacting with that. I'm reacting ethanol with hydrogen cyanide. So what molecule am I going to make in the middle there? Well, the first one I'm going to make is the hydroxynitrile. So it's going to add like so, the C and the H then. So the key thing is you've got 3 carbons in lactic acid, but only 2 here. And that's the key benefit of using a cyanide because you increase the carbon chain length. What reagent could be used for step 2? Well, this is reacting it with aqueous acid. So H plus aqueous. Displayed formula of lactic acid is shown below. Suggest a value for the bond angles. Okay, so this is going back to your AS chemistry. So let's have a look. There's carbon for A, 4 bonding pairs, no lone pairs. So that is, of course, 109.5. For B, hopefully you can just see this is just going to be like water with an H there. 2 lone pairs, 2 bonding pairs. That is, of course, 104.5. And finally C, 3 bonding pairs, no lone pairs. That is going to be trigonal planar and 120 degrees. Right, so methyl lactate is an ester of lactic acid. Okay, I can hydrolyze this with sodium hydroxide and it reacts as a nucleophile. How can the hydroxide ion act as a nucleophile? What is a nucleophile? It is an electron pair donor. So the hydroxide ion is an electron pair donor. Pattern mechanism is shown below. Add the relevant dipoles and show how we can get that. So if we go step 1, can you see that I'm adding my OH here and I've broken the double bond there. So this bond is going to be polarized, delta plus, delta minus. You are then going to have a lone pair of electrons on that O there. That is going to go there and that bond is going to go there to form your intermediate. You've then got to lose the methoxide ion there and that works by that going there, my lone pair of electrons going back to form my double bond like so. Okay, so this may freak you out because you may think, oh no, I've got all sorts of functional groups going on here and I'm reacting it with a acid chloride, an acyl chloride molecule, which is of course ethanoyl chloride. Well, okay, just think back to your chemistry. This is an ester. Do you know anything about acid chlorides reacting with esters? And the answer would be no. However, you do know about them reacting with alcohols. So just go through what you know. You've got a CH3, C double bond O, which is this bit here. And then you're going to lose the Cl, and that's O is going to be that O there. And then just draw the rest of the molecule like so. And you've made yourself another ester bond like so. And your other product, of course, is going to be HCl. Okay, so compound F, molecular formula is C4H8, so is obviously going to be an alkene. And that gives us more information because we react it with steam to form 3 alcohols. Alcohol G must be is reacted with acidified potassium dichromate to form J, and J reacts with Tollens reagent to form K. So first of all, J must be an aldehyde from that information, which means that compound G is going to be a primary alcohol. So it looks to me like we have got compound F as being CH3, CH2, CH double bond CH2. And then you can, of course, add water. You could either add an H and an OH there or an H and an OH there. So you're going to give you CH3, oh sorry, that should be CH2. CH2, CHOH, like so, CH3. And then you've also got CH3, CH2, CH2, CH2OH, like so. Okay, now this guy here has got a chiral carbon there, so I'll draw him in a minute. I run out of a bit of space, but this is going to be F. This guy is going to be G, isn't he? J I haven't got to, so J is going to be my aldehyde. So that's going to be CH3, CH2, CH2, CHO. So that is J. K is going to be the carboxylic acid. Crikey. So I'm going to have to go down here now. CH3, CH2, CH2, COOH is K. And then I'm going to draw these in 3D. So I'm going to have my H there. I could have my OH there. I'm going to have my CH3 there, and then going back I'll have my CH2, CH3, and then we can just swap two of these around. Let's keep those the same, but let's swap that to be CH2, CH3, and this guy to just be my CH3. And those are my two optical isomers H and I, like so. Now you can have a think about your options that it could have been. It could have been butene that you started with, but if it had been butene, you wouldn't have actually made different isomers because because it's symmetrical. It wouldn't matter which way your H and OH added. The other one it could have been is methylpropene, but if you go that way, the rest of the reactions it won't make sense in terms of making optically active alcohols and so on. It just won't work. So the next B is how can I identify J with a chemical test? So J is an aldehyde. So as you know, with carbonyl compounds, you can add 2,4-dinitrophenylhydrazine and you will get a orange precipitate. You then recrystallize that precipitate and take its melting point of the crystals, and you compare that melting point to known values in a data book, and that will identify the original aldehyde that you started with. Okay, so I've now got compound L that I'm starting with down here. And I'm going to react with HBr, but we've got to get eventually to this molecule here. So hopefully you can see that I've added an alcohol group here, which means in this reaction 1, I need to add the Br to that carbon there. So I'm going to make C6H5, and then I'm going to have my Br there, where I've added it. Doesn't really matter for the rest of it stays the same because you have not been taught anything about HBr reacting with a benzene ring or a carboxylic acid. You just know it does electrophilic addition. Excess ammonia is you're going to do a nucleophilic substitution for your bromine there. So you're going to have C6H5, and then that is then NH2, like so. The rest of it stays the same, you haven't touched that. NaOH, well, that there is going to give you C6H5, but then you're going to do a nucleophilic substitution with your bromine to give you OH. However, you are now in alkaline conditions, so you are going to deprotonate your carboxylic acid like so. And then finally your H plus will just take that to give you back your carboxylic acid. Okay, so here we go. Gonna do an electrophilic addition now. The electrons are going to come out of my double bond, go to form a bond with the hydrogen, and that bond is going to break like so. So I end up with C6H5. You've then got your positive charge on that carbon there. Your hydrogen's added to that carbon of the double bond there. You're left with Br minus dot with your lone pair of electrons there, which is going to go to that carbon there to give you your product like so, which is what you made. Just remember to make sure your bromine adds to the correct carbon. It's very easy to get it mixed up the wrong way, so you've got to get this step right here to make sure that your hydrogen adds to that carbon there, like so. Okay, the name of the mechanism, of course, is electrophilic addition. Okay, so back to polymers. Okay, so here we go. All I've done is I've drawn compound M, but I've drawn it as an H shape around this double bond here, which hopefully you can see. If you remember, you've got an H coming off that carbon there and an H coming off there, like so. So the way it's going to work is that that's going to be your repeat unit, like so. Okay. Of the condensation polymer, that's going to be quite tricky. So I'm going to draw it and then it will appear in a minute. Right, so it wants me to do two repeat units. So I've drawn two molecules of compound M and it's going to make a polyester. So what I've done is I've set up the alcohol and the acid nicely to do that. And then we're going to eliminate water. So let's get rid of the H from there and the OH from there. And then that is going to give me my first new bond from there to there, like so. And then we're going to get rid of, do the same here, we'll get rid of that H there and the OH there. And so we're going to have this bond like so, and then that bond like so. And that gives you your two repeat units. Okay, so we're now going to break down this artificial sweetener by acid hydrolysis. So we're going to break all our ester bonds and our amide bonds. So that one's going to go there, that one's going to go there. Any more that you can see? I can't see any at the moment, so we will draw those molecules out with those breaks in. Right, so I've drawn those molecules there without those breaks. So now we just need to remember that we're in acid conditions. So because we're in acid conditions, that is going to become a carboxylic acid there. That will become my alcohol. We're going to protonate this nitrogen there to become a plus. That's going to become my acid there. And then this N will also become protonated with a plus charge, like so. Right, so last question, we have to identify this compound here. So start with the elemental analysis, and you can see I've done that at the top there, up here. If you do the empirical formula, you will end up at being C5H10O2. They told me my molecular ion peak, and if you add up 5 carbons, 10 hydrogens, and 2 oxygens, you get 102. So that is my molecular formula. Checking out my IR now, well, this is just CH here, so nothing particularly exciting there. However, this guy here is C double bond O there, so we have got C double bond O in the molecule. So, you know, we're probably thinking ester, aren't we, here? So let's have a look now at my hydrogen NMR, and this is where things will really start coming together. Quite simple in a way, but let's have a look. So first of all, it told me that this peak here should be at 3.9, and if it is, then it is this group here. Now, okay, I've only got one hydrogen in that environment attached to a carbon which is attached to an oxygen, but it's split into 1, 2, 3, 4, 5, 6, 7 lines, so it must have 6 neighbours. And have a look at this peak here. You've got a peak of intensity 6 into a doublet. So that suggests to me I have got this going on here. Like so. Okay, now the next logical step is going to be C double bond O, like so. And then I've got this final group here, so intensity 3. So I must have this going on here. So a CH3 group like so. So I'll draw it out on the next page so you can see it in its full glory. So you are going to have CH like so, then 2 methyl groups coming off like so. Then you've got the oxygen, then you've got C double bond O, and then you've got a methyl group like so. Okay, and in your answer, it's really important that you explain it in terms of this hydrogen here having 6 neighbours, this not having any neighbours, these guys having 1 neighbour, which is why they're split into a doublet, and so on. Okay, but it's not too bad a molecule to sort out.